Hi, we're going to talk about L'Hopital's rule, and this is not a video on deriving it. This is just going to be a video on how to use it, and I'm going to work about 17 problems, I think. Yep, 17 total, and the first time I recorded this, it didn't record, so I'm a little aggravated, so bear with me. We want to talk about indeterminate forms. So in order to use L'Hopital's rule, you have to be of the form 0 over 0 or some plus or minus infinity or plus or minus infinity. Now, other forms that are indeterminate are infinity minus infinity, which you might think is 0, but it's not all the time. 0 times infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. And I'm going to do several examples that where we have this indeterminate form and we transform it into the form that we can use for L'Hopital's rule. Now, some limits that are determinate are, for example, if I have infinity plus infinity, well, guess what? That's just still infinity. And negative infinity minus negative infinity then is also negative infinity because we just multiplied this result by -1. 0 to the infinity is just 0, and 0 to the negative infinity is infinity. And I want you to think about 1 over x. Right? And as x goes to 0, what happens? Well, you're headed towards infinity, and that's why that's 0 to the negative infinity. All right. So if I'm speaking a little fast, it's because I've already spent an hour doing this once. So here we go. All right, so we're going to start off with some basic ones first. So number 1, the limit then, as x approaches 0 of sine x over x, which is 1 we know for sure, but I'm going to show you now that the algebra behind it works. Okay, so first we have to determine if we are, pardon the pun, in the form of 0 over 0 or infinity in order to use L'Hopital's rule at all. And what happens here is when I plug in 0 for x, I get 0 over 0. And I can, you notice I don't put an equals here because this limit doesn't equal 0 over 0. It turns out to be something else. So I can use L'Hopital's rule now. And that rule states if you have an indeterminate form of 0 over 0 or infinity, I can say that the limit is equal to the limit of the rate of change of the numerator over the rate of change of the denominator. So I'm going to take the derivative of the numerator and get cosine x, and the derivative of the denominator is 1. And now, can I plug in 0? Well, the answer is yes, and the cosine of 0 is just 1. All right, so that's my first one. And we were able to verify this graphically when we first figured out what that limit was a long time ago. All right, number 2. The limit as x approaches 0 of sine of 3x over the sine of 4x. Now, before we knew about L'Hopital, we would have had to use some fancy trig identities here, like the sign of a sum, to bust this up and somehow try to use trig identities to be able to solve this limit. So in order to solve this limit, what we're going to do is see if it's one of our indeterminate forms. So when I plug in 0, I get 0 over 0 because the sine of 0 is 0. And, so it's 0 over 0. So I can use L'Hopital here. And we'll get the limit then as x approaches 0 of, well, we have to take the derivative of the numerator using the chain rule. So what happens when I use the chain rule? Well, that derivative of the numerator is going to be 3 cosine of 3x. The derivative of the denominator is going to be 4 cosine of 4x. And what happens when I plug in 0 now? Well, I get the cosine of 0. 3 times the cosine of 0 is 3, and 4 times the cosine of 0 is 4. So this limit is 3/4. So in this case, I have a 0 over 0 equaling 1, and a 0 over 0 equaling 3/4, which is the reason why 0 over 0 is indeterminate, because it could be a myriad of different answers. All right, number 3. The limit as x approaches pi of x minus pi over sine x. All right, so what happens when we put in pi into our expression here? Well, pi minus pi in the numerator is 0. The sine of pi is 0. So now I can use L'Hopital's rule, which states that the limit's going to be equal to the ratio of their rates of change. So what is the derivative of the numerator? Well, that's just 1 over the derivative of the denominator, which is cosine x. And now I can plug pi in, and the cosine of pi is -1. So this turns out to be 1 over -1, or just -1. All right. Number 4. The limit as x approaches 0 of x minus sine x over x cubed. So what happens when I plug in 0? Well, I get 0 minus 0 over 0. So I can use L'Hopital's rule here and take the limit of their rates of change. So the derivative of the numerator is going to be 1 minus cosine x over 3x squared. All right, well, so what happens now when I use substitution to plug in 0? We get the cosine of 1, which is, cosine of 0, which is 1. So 1 minus 1 is 0 over 0. Oh, no. The good news is with L'Hopital's rule, which we love, we can do it more than once, because now we can do this ratio. And we can use L'Hopital's rule here, do it one more time and see what we get. So the derivative of the numerator is going to be 1 minus, the derivative of negative cosine is positive sine over 6x. Well, oh no, not again. It's 0 over 0. So one more time. The limit as x approaches 0 of, what was the derivative of sine? Well, it happens to be cosine. And then the derivative of 6x is 6. And now I know I am no longer going to have an indeterminate form. So let's see what happens when I plug in 0. Using direct substitution, I get 1/6. So that limit is 1/6. All right, moving along. Now we're on number 5. All right, number 5. Let's try this one. The limit as x approaches 0 of e to the 3x minus e to the 5x over x. All right, so what happens when I plug in 0? Well, e to the 0 is 1. So this turns out to be 1 minus 1 in the numerator. And so that is 0 over 0. Not a big surprise, because this is L'Hopital's lesson anyway. So I'm going to take the derivative of the numerator and the denominator. And the derivative of e to the 3x is 3e to the 3x minus 5e to the 5x all over 1. And I now know I don't have an indeterminate form because I have a 1 in the denominator. And I can use direct substitution to plug in 0 now. And 3 times e to the 0 is 3, minus 5 times e to the 0 is -5. So the answer is going to be -2 here, because 3 minus 5 is -2. Really nice limits here. All right, number 6. The limit as x approaches 0 of tangent of x minus x all over sine x minus x. And what happens when we plug in 0 by direct substitution? We would get the tangent of 0 minus 0 over the sine of 0, which is 0 minus 0. So we get 0 over 0. So we can use L'Hopital's rule. And we get the limit then as x approaches 0 of, well, what's the derivative of the numerator? Well, the derivative of tangent is secant squared x, and the derivative of x is 1. So it's secant squared x minus 1 over the derivative of sine x, which is cosine x, minus derivative of x, which is 1. And I know I hear you guys in the back of the room shouting, Mrs. Muller, that is something. And you're right. This secant squared x minus 1 is tangent squared x, and I would like to change that. So we're going to say the limit as x approaches 0 of tan squared x over cosine x minus 1. And whether that's simpler or not, I don't know, but Most people don't like to take the derivative of secant squared x, but we're going to have to do that later in this video. So just let's keep that in mind. But in this case, let's see what happens when we plug in 0. When we plug in 0, we're going to get 0 over 0, because the cosine of 0 is 1, and 1 minus 1 is 0, and the tangent of 0 is 0. So we can use L'Hopital one more time, and the limit then, as x approaches 0, we have to use the chain rule. So we're going to go power down, function, which is tangent, lower the power 1 times the derivative of the inside, which is secant squared x, all over the derivative of cosine, which is negative sine x, and the derivative of 1 is just 0. Now, I would have to use this is 0 over 0 again, because the tangent of 0 is 0 and the sine of 0 is 0. So this right here is going to be a little bit messy because I'd have to use the product rule here, but I'm going to use my understanding of trig functions and simplify this first. So this is going to be a simplifying step. So this is going to be 2 times, well, what is tangent? Well, tangent happens to be sine x over cosine x. Secant squared happens to be 1 over cosine squared x. And this denominator is really sine x over 1. So when I flip it, I get 1 over negative sine x. And then let's simplify this by, removing what we can remove. And so then this limit breaks down into negative 2, because there's a negative down here, over cosine cubed x, which is nice because I can plug 0 into cosine, and when you do that, you get 1. So this limit turns out to be negative 2. So when using L'Hopital, sometimes it's nice in the middle to do some simplifying using your trig identities that you know to simplify your answers. All right? So that's number 6. Let's move on to number 7. Number 7. All right, here we go. The limit as x goes to infinity. I've changed it up now. We're going to go towards infinity of x to the 5th over e to the 5x. Now, what happens as I let x go to infinity on this nice, lovely ratio? Well, x to the 5th goes to infinity, and so does e to the 5x. So I can use L'Hopital here and find the limit of their rates of change. So what's the derivative of x to the 5th? Well, that's just 5x to the 4th over the derivative of e to the 5x, which is 5e to the 5x. And these 5's can cancel, which is really nice. And I'm left with x to the 4th over e to the 5x. And the rate of change, well, I'm sorry, as x goes to infinity, we get infinity over infinity because x to the 4th gets large, and so does e to the 5x. Oh no, I have to do it again, this L'Hopital's thing. All right, so the limit as x goes to infinity of, well, that's 4x cubed over 5e to the 5x, sorry. And I can hear you groaning in the background saying, oh no, Mrs. Muller, we're going to have to keep doing this. We're going to have to keep doing this for a while because that x to the 3rd, right? Well, yes, and for the purposes of this video, I'm going to go all the way. But eventually, I know what you're thinking, this 4x to the 3rd is going to differentiate to a constant, and then we won't use L'Hopital anymore. But thank goodness I didn't do an example of e to the 100 over e to the 5x. So let's be thankful for that. All right, so we're going to do L'Hopital's one more time. The limit as x approaches infinity, well, that's going to be 12x squared over 25 e to the 5x. I almost wrote x again. And guess what? Whoa, not surprising. That's infinity over infinity again. And please note, I'm not putting equal signs here because they are not equal. This is just the indeterminate limit type. All right, using L'Hopital's one more time. The limit as x goes to infinity of 24x over, well, 5 times 25 is 125 e to the 5x. And again, that's infinity over infinity, so I can use L'Hopital's rule. The limit as x goes to infinity of, this turns out to be 24 over 625 e to the 5x. And now I can say with complete confidence that this limit right here is going to go to 0. Okay? That limit's going to go to 0. Why? Because the denominator is going to get incredibly large and the numerator stays constant. Okay. So I just want to do a generalization. The limit as x goes to infinity of any polynomial x to the n over e to the kx, no matter what k is, and I'm going to say k is a constant here. K greater than 1. Well, no, greater than or equal to 1. Greater than or equal to 0. Let's try that. No, not greater than or equal to 0. Just k greater than 0. Because if it's equal to 0, then we have 1, and that goes to infinity. So k greater than 0. K greater than 0 is going to go to 0. That's because the exponential function grows faster than the polynomial function. And conversely, the limit as x goes to infinity of e to the kx over x to the n, same restriction here. This one is going to go to infinity because e to the x grows faster. Okay? So that's a good thing to remember. And if you know these things, do you have to do this on a multiple choice infinitely many times? The answer is no. If you know that you have a polynomial on top, you know that this is going to approach 0. Okay? All right. We're on to number 8. I feel like I'm speed talking, but that's okay. The limit as x approaches infinity of the natural log of x over x. Well, both of these functions, as x gets really large, go to infinity. So this is infinity over infinity. And I can use L'Hopital's rule here and say the limit then, as x goes to infinity of, well, I have to take the derivative of the numerator, which is 1 over x, over the derivative of the denominator, which is 1. And this is the same thing as saying the limit as x approaches infinity of 1 over x, and we know that is 0. And again, this means that the natural log function doesn't grow as fast as y equals x. Not a surprise. All right. Now this is one of my favorite limits. And this is number 9. And this is the limit then as x approaches infinity of 1 plus 1 over x raised to the x. Now this is a function of x raised to another function. And so when you have this situation, we have to set this limit equal to y, and we have to get this exponent down somehow. How do we do that? Well, naturally, we take the natural log of both sides. And that's going to be the natural log of y equals the limit as x approaches infinity of, and I'm going to say that this is 1 plus 1 over x raised, natural log, of this raised to the x. All right, so I'm just going to forget about this side until the very end. So I haven't forgotten about it, but we're going to use it at the end. So what can I do with this exponent? I can bring it down in front, so I get x natural log of 1 plus 1 over x. And what happens as x goes to infinity? Well, I get infinity here times, well, this term here, as x goes to infinity, goes to 0. So this is the natural log of 1, which is 0, which is one of those indeterminate forms I spoke about in the beginning of the video. So I have to do some math magic here to get it into the form of 0 over 0, or infinity over infinity. So this is what you do. You take the limit as x goes to infinity of natural log of 1 plus 1 over x, and you take this x and you move it to the denominator by making it its reciprocal. All right, and that's a technique that you have to use to solve this one. So what happens now when x goes to infinity? This term still goes to 0, and we get the natural log of 1, which is 0, over, and then 1 over x, as x gets really large, goes to 0. And so now we're in the form of 0 over 0, and we can use L'Hopital's rule, okay? So let's do that. Well, we have to refresh our memory then on what the derivative is of a log. Well, the derivative of a log is f prime of x over f of x. So I'm going to take the derivative of the f of x in here, which is going to be the derivative of 1 is 0, the derivative of 1 over x is negative 1 over x squared. So that goes in the numerator over 1 plus 1 over x divided by the derivative of 1 over x, which I just took, which is negative 1 over x squared. All right, so let's do some simplifying. That's going to equal the limit as x approaches infinity of negative 1 over x squared over 1 plus 1 over x times negative x squared over 1 if I flip the denominator. And what's really nice is these go away, and I'm left with the limit as x approaches infinity of 1 over 1 plus 1 over x. And as x gets really large, what happens to this 1 over x? Well, this 1 over x goes to 0, and I'm left with 1. But you might think the limit is 1, but we can't forget about our natural log up here. So we're going to take it and bring it all the way down and say, but wait a minute, it's the natural log of y that equals 1. So I have to undo the natural log that I took originally by exponentiating both sides, and I get y equals e. So the limit as x approaches infinity of 1 plus 1 over x raised to the x is equal to e. Now, that's that famous limit that we learned about in pre-cal so long ago. And then this is the mathematics using L'Hopital on how to find it mathematically, which is pretty cool. I think anyway, in the nerd universe. Okay, so let's go on to number 10. Number 10, the limit as x approaches 0 from the plus side of sine x raised to the x. All right, here we go. This is of what form? Well, this looks like this is 0 raised to the 0, which is one of those indeterminate forms I mentioned at the beginning of the video. But then again, I have this function here raised to a function, so I have to make this equal to y. And then in order to get that exponent down in the front, I have to take the natural log of both sides. So I get natural log of y equals the limit as x approaches 0 from the plus side of, and I'm going to take the liberty of bringing the exponent down, x natural log of sine x. And then what happens to this side? What form are we in? Well, what happens as I take x to 0? I get 0 times, well, we need to remember what the sine function looks like. Well, the sine function looks like this. And as x approaches 0, our sine function is approaching 0. So this means that I'm approaching the log of 0, which is negative infinity. So since the sine function is approaching 0 on the inside of the argument here, that means the log is approaching the log of 0, which is negative infinity. So this is that indeterminate form, 0 times some form of infinity. And we have to do some math magic to get it into a fraction, 0 over 0 or infinity over infinity, so that we can use the L'Hopital's rule. So what are we going to do? We're going to take this x and we are going to move it to the denominator naturally. And then what do we get? Well, we get the natural log of sine x is approaching negative infinity, and 1 over x, if you think of the graph, as you approach 0 from the right side, is approaching infinity. So now we can use L'Hopital's rule. And that's the limit then is equal to the limits of their rates of change. Well, what is the derivative of a log? Well, it's the derivative of the argument, which is cosine x, over the argument, which is sine x, divided by, here, I'm going to take the derivative of the denominator, which is negative 1 over x squared. And I'm not going to use L'Hopital's right away. Let's do a simplifying step. Let's see what happens. We get the limit as x approaches 0 from the plus side of, this turns out to be negative x squared cosine x. I like to put the polynomials in front of my trig functions. All right. All I did was reciprocate the denominator and multiply. Now, what happens when I plug in 0? Well, sadly, I get 0 over 0. And then I have to use L'Hopital's rule. Oh no, but Mrs. Muller, this is a product. Yes, it's a product. So we have to use what? The product rule. That's right. So we're going to say first, which is x squared, times the derivative of the second, which is negative sine x, plus second, which is cosine x, times the derivative of the first, which is negative 2x. All over the derivative of the denominator, which is just lonely old cosine x. So I don't have to simplify this. I can just substitute in 0 and see what happens. When I plug in 0, the first term here goes to 0. And when I plug in 0, this one goes to 0. Okay, that's great. But what about the denominator? What happens when I plug in 0 into cosine? Well, the cosine of 0 is 1. So this is no longer indeterminate. It's just 0 over 1, which is 0. But I can't forget so long ago that I took the natural log of both sides. So I have to bring that down. And I get the natural log of y equals 0. So I have to exponentiate. And I get y equals 1, which means the limit as x approaches 0 from the plus side of sine x raised to the x is equal to 1. There you go. All right, so sometimes you have to use the product rule in our attempt to use L'Hopital's. All right, that's number 10. So we've done a 0 to the 0. Oops, I forgot to tell you that this one here, the E one is 1 to the infinity, because what happens when I plug in infinity? This goes to 0, and so I get 1 to the infinity. So that's the indeterminate form on that one. Okay. Let's do number 11. Number 11. The limit as x approaches 1 from the plus side of 1 over natural log of x minus 1 over x minus 1. All right. So remembering what the natural log graph looks like, it looks like this. And the curve 1 over x minus 1, that's got an asymptote at 1. And it's just the 1 over x function, right? Shifted to the right by 1. Okay, so let's see what this one is. This one is we're approaching the natural log function is approaching 0 at 1, isn't it? So this is really like 1 over 0 from the plus side. So this is going to be infinity minus infinity. And if you have trouble seeing that, come and see me and we'll talk about how that works. But this is actually infinity minus infinity, because this one's easier to see, that you see that it's going to infinity here. This one is harder to see because the log is approaching 1. Well, what the log is approaching 0 from the positive side, right? It's a natural log of 1, right? It's approaching 1, but the denominator is approaching 0 from the positive side, which is actually infinity. So anyway, moving right along. I have to get it in a fraction form in order to use 0 over 0 or infinity over infinity. That's indeed what it turns out to be. So the strategy on this one is to find a common denominator, which is at natural log of x times x minus 1. So I have to multiply this fraction by x minus 1 minus, and I multiply this fraction by natural log of x. So what happens when I plug in 1? we get 1 minus 1 minus the natural log of 1, which is 0, and the natural log of 1 on the bottom here is 0. So this is 0 over 0. Using L'Hopital here, I'm going to get the limit as x approaches 1 from the plus side. Well, the numerator's derivative is going to be 1. The derivative of negative 1 is 0 minus 1 over x, which is the derivative of the numerator. And then, yes, I hear the moans and groans from the back. We have to use a product rule in the denominator. So it's going to be first times the derivative of the second, which is 1, plus second, which is x minus 1, times the derivative of the first, which is 1 over x. So let's simplify a step. The limit as x approaches 1 from the plus side of, well, this is 1 over 1 minus x, 1 minus 1 over x, and then this is going to be the natural log of x plus 1 minus 1 over x. Now, I don't love to have these double-decker fractions, so I'm going to multiply this by x over x. And I'm okay with that because x is not approaching 0, it's approaching 1. So I'm not multiplying by 0 over 0. So here we go. The limit as x approaches 1 from the plus side of, what happens to the numerator? I get x minus 1 over x, natural log of x, plus x minus 1 in the denominator when I distributed it all out. But sadly, that still gives me this 1 minus 1 here is 0, and the natural log of 1 is 0. So I have 0 over 0 again, so I have to use L'Hopital one more time because I know the derivative of the numerator here is 1, so I'm not going to have to use it again. So there's sunshine on the horizon. So the derivative of the numerator is 1 over the derivative of the denominator. Yes, I have to use a product rule. So it's first d second plus second times the derivative of the first, which is 1 plus 1, because the derivative of x is 1 and the derivative of negative 1 is 0. And now what happens? We get the limit as x approaches 1 from the positive side of 1 over 1 plus the natural log of x plus 1. And now I can plug 1 in happily because the natural log of 1 is 0. But then I get 1 over 1 plus 1, which is 1/2. So infinity minus infinity is equal to 1/2. That's why this is indeterminate. You would think it would be 0, but it's not. It's 1/2. So which one is bigger? Well, this fraction is bigger than this one because I got a positive answer, which is kind of cool. All right. I'm going to do another infinity minus infinity. And it's an interesting one, I think, because sometimes L'Hopital's rule isn't always the best. Here we go, number 12. We're going to take the limit as x goes to infinity of the square root of x squared plus 5x plus 2 minus x. Now, this is going to be the square root function going to infinity, and this one is going to infinity. So this is another infinity minus infinity. So somehow we have to get a fraction out of all this madness, and I can't just divide by the reciprocal because I don't, they're not multiplied together. So I have to use some math magic that we're familiar with square roots, which is use of the conjugate. So I'm going to multiply this by the conjugate of this, which would be the square root of x squared plus 5x plus 2 plus x. But since I don't want the expression or the limit to change its value, I'm going to multiply it by the conjugate factor of 1. So I'm actually multiplying this by 1 of my choosing, right? It's such a pretty factor of 1 too, isn't it? Anyway, all right, here we go. What happens when we multiply by the conjugate? Well, we get up here we get the factors of the difference of squares. So this is a squared minus b squared. So when I square the square root, it just takes the square root off, and we get x squared plus 5x plus 2 minus x times x, which is x squared, all over the square root of x squared plus 5x plus 2 plus x. And the x squareds cancel, and I'm left with the limit as x goes to infinity of 5x plus 2 over the square root of x squared plus 5x plus 2 plus x. Now, you would think that using L'Hopital's rule here, because these both are going to be infinity over infinity, would be helpful. And you think it might go to 1, but you don't know it'll go to 1, or it could go to something else. But in this case, if I were to take the derivative of the top, that would be really easy. That's 5 over the derivative of the bottom of the denominator, which would be 2x plus 5 over 2 root x squared plus 5x plus 2 plus 1. So this turns into a double-decker fraction in the denominator, and then you'd have to find a common denominator, which would have a square root in it, which would put the square root on top. And then you have square roots in the numerator and the denominator, and they just don't ever go away. So I hope you take my word for it. And if you ever have one of these, this is the math that you should use, the algebra, to do this limit. So I wouldn't use L'Hopital's rule here. It makes it infinitely more difficult, if not impossible. So the first thing I'm going to do is the thing that you would least expect. Of course it is, right? I'm going to take and factor out an x in the numerator. And what do I get when I get that? I get x times 5 plus 2 over x divided by, now it's going to take me a couple of steps to take care of the denominator. But under the square root, I'm going to factor out an x squared. And when I do that, I get 1 plus 5 over x plus 2 over x squared. And you'll know I'm right. If you were to multiply this x squared back in, you get x squared plus 5x plus 2 plus x. And I can take out an x out of this underneath this square root now, because I have an x squared there standing alone saying, take the square root of me. And since x is positive and we're going to infinity, I don't have to take out an absolute value of x. So we're going to get x in the numerator plus, times 5 plus 2 over x over x times the square root of 1 plus 5 over x plus 2 over x squared plus x here. And now in the denominator, do you see how I can factor out an x? So we get the limit then as x goes to infinity of x times 5 plus 2 over x in the numerator over x times the square root of 1 plus 5 over x plus 2 over x squared plus 1. And now I can cancel these x's out. And I'm left with a limit that's much more doable. So this is 5 plus 2 over x over the square root of 1 plus 5 over x plus 2 over x squared plus 1. And now what happens to these terms that are over x and x squared as x goes to infinity? Well, this gets to be 2 over something very large, 5 over something very large, 2 over something even larger. And these terms, this goes to 0, this goes to 0, this goes to 0. And I'm left with 5 over the square root of 1 plus 1, which is just 5 halves. All right, so in that case, it looked like I might want to use L'Hopital, but the algebra is the way to go on this one. Okay? All right, so infinity minus infinity, not equal to 0. It's equal to 5 halves. All right, number 13. This is one I like to do because I've seen these on multiple choice questions before, so they're very worth knowing how to do. So I'm going to put an integral, an area accumulation function, oh no, on top in the numerator. And let's see if this is indeterminate. What happens when I plug in x equals 1? Well, I get an integral from 1 to 1, which is, as we all know, 0. And then when I plug 1 in the denominator, I get 0, so we get 0 over 0. So I can use L'Hopital. And this is a nice review of the fundamental theorem of calculus, because now I'm going to take the derivative of an integral, which is equal to the function cosine of theta evaluated where I stopped, which would be at cosine x. over the derivative of x minus 1, which is just 1. And now I can plug in 1. And my solution then is going to be just the cosine of 1. And I don't know what that is. And 1 in radians. It's going to be somewhere in the first quadrant. But cosine of 1 is our limit. This is a kind of a cool one because it reviews the fundamental theorem of calculus and the derivative of that integral. All right, number 14. Number 14, y equals the limit as x approaches 1 from the plus side of the natural log of x raised to the x minus 1. Now I took the liberty of making this y equals already because I have a function raised to a function. And what happens if I plug 1 in here? Well, I get the natural log of 1 is 0, and this one is 0 to the 0. So we're going to see if 0 to the 0 equals 1 or something else, or 0. All right, so what do we do when we have a function raised to a function? Oh, I hear somebody whispering in the back saying, oh, we could take the natural log. Oh, yeah, you do. You take the natural log of both sides. So this is the natural log of y equals the limit as x approaches 1 from the positive side of, and I'm going to take the liberty of taking this x minus 1 and bringing it down in front. So we get x minus 1 times the natural log of x. All right, now let's see what this situation is. When I plug in 1, I get 0. 0 times, okay, well, I plug 1 into this natural log and I'm approaching 0, and the natural log of 0 is negative infinity. So the technique when we have 0 times infinity is to move something to the denominator, and I always choose to move the polynomial factor. So we get the limit then as x approaches 1 from the plus side of the natural log of x, which is such a pretty function, over 1 over x minus 1. And now what happens? We already know that the numerator we said approaches negative infinity, and the denominator, let's see, that's going to approach infinity because we did that graph a moment ago, and that's just the 1 over x graph shifted to the right by 1. So we know that that's going to infinity. So now I can use L'Hopital. The limit as x goes to 1 from the positive side of, well, I have to take the derivative of a log of a function, which is going to be f prime over f of x. So it's going to be 1 over x over the natural log of x over the derivative of 1 over x minus 1, which is the same thing as saying x minus 1 to the negative 1, which would be negative x minus 1 to the negative 2 times the derivative of the inside, which is 1. So this is negative 1 over x minus 1 quantity squared. Oh, these fractions everywhere surrounding me. Oh no. The limit as x goes to 1 from the plus side of, let's do some simplifying. The numerator becomes 1 over x natural log of x. Before we freak out about that, that's 1 over x times the natural log of x. We're reciprocating natural log of x over 1, which is 1 over natural log of x. So that's the numerator here. Times x minus 1 quantity squared over negative 1. If I flip the denominator. All right, so then we get the limit as x approaches 1 from the plus side of negative x minus 1 quantity squared over x natural log of x. I didn't forget my negative side, which is nice. Oh no, we get 0 over 0. This is so much work. So we're going to use L'Hopital again. I got to use the product rule here. Limit as x goes to 1 from the plus side of, well, what's the derivative of the numerator? Got to use the chain rule. Negative 2, power down, function, lower the power 1, times the derivative of the inside, which is 1, all over first, the second, plus second, hallelujah, the first is 1. So we get the limit as x approaches 1 from the plus side of negative 2 times x minus 1 over 1 plus the natural log of x. Well, the good news is that the numerator is 0, but the denominator is 1. So this equals 0 over 1, which is equal to 0. Not indeterminate anymore, and I got to lasso this natural log of y. I got to remember that back in the beginning, I took the natural log of both sides and bring the natural log of y here, and then exponentiate, and I get y equals 1, which means my limit as x approaches 1 from the plus side of the natural log of x raised to the x minus 1 is equal to 1. And because this was kind of an interesting function, I took the liberty at the beginning, before I started the video, to show you guys, I wanted to show you guys that the graph does indeed approach 1. If you look at it from the positive side, it is 1, which is kind of cool. All right, we're getting there. Moving along here. All right, number 15. All right, these are the ones from my test. The ones that were so hard. Now let's see, after looking at some of these other ones, whether we think these are not as hard anymore. All right, so what is this limit as x approaches infinity? Well, we get infinity times the sine of 1 over infinity, which is the sine of 0, which is 0. So this is that form that, what do I have to do? I have to change this into a fraction using the math magic. And I always move the polynomial because it's easier to do, in my opinion. Make this 1 over x in the denominator. And now what happens is I have the limit as x goes to infinity. This becomes a sine of 0, which is 0, and 1 over x as x goes to infinity is approaching 0. So this is 0 over 0. Now I can use L'Hopital's rule, get the limit as x approaches infinity of, well, this is composite, so I got to use the chain rule. So this is going to be the cosine of, keep the argument, times the derivative of the argument, which is negative 1 over x squared, all over the derivative of the denominator, which is, lo and behold, negative 1 over x squared. And these two things cancel, and I'm left with the limit as x approaches infinity of the cosine of 1 over x. And this is approaching the cosine of 0, which is 1. So that one wasn't as bad as folks maybe thought. I don't know. But all right, here we go. Number 16. The limit as x approaches 0 of x times the tangent of x over 1 minus the cosine of x. So what happens here when I plug in 0? Well, that's 0 over 1 minus the cosine of 0 is 1, so 0 over 0, so we can use L'Hopital's rule here. And yes, I have to use the product rule in the numerator. So I use first, which is x, d second, the derivative of tangent is secant squared x, plus second, which is tangent, times the derivative of the first, which is 1. Great. Done with the numerator. Now, the derivative of the denominator, the derivative of 1 is 0. The derivative of negative cosine is just regular old sine. Oh, no. When I plug in 0, I get 0 over 0. Because the tangent of 0 is 0, and a 0 here, and the sine of 0. So, yes, I have to use the product rule again in the numerator, using L'Hopital's rule. Limit as x approaches 0, it's going to be first. And yes, this is a trig function raised to a power. So I have to go power down, function, lower the power 1 times the derivative of the inside, which is secant. So that's secant x, tangent x, plus second, which is secant squared x times the derivative of hallelujah, the first is 1, plus the derivative of tangent, which is secant squared x. Oh man, that was a lot, huh? All over the derivative of sine, which is positive cosine. Now, what happens when I plug in 0? Well, this term goes to 0. And these two, the cosine of 0 is 1. So I know the denominator is 1. And the secant is 1 over the cosine. And the cosine is 1. So this is 1 plus 1. So this limit is 2 over 1. Okay? So what maybe made that one difficult was finding the derivative. I don't know. Number 17. Actually, this is going to have 18 of them. So sorry, one more after this. The limit as x approaches pi over 2 from the left side of x tangent x minus pi over 2 times the secant of x. All right, so pi over 2. If we recall back in the day when we were graphing tangent and secant, yes, oh, were those the days. They both have asymptotes of pi over 2. So the tangent graph is approaching pi over 2 from the negative side. That's infinity. And then the secant graph is also approaching pi over 2. So this is really infinity minus infinity. And somehow I have to get them into fractions. Well, the good news is that tangent and secant have fractions implied in them because I can change them into their sine and cosine composite parts. Okay, so then we get x times the sine of x over cosine x, right? Because tangent sine over cosine, minus pi over 2 cosine x. Because secant is 1 over cosine. And now I can find a common denominator, which happens to be 2 cosine x. I have to multiply this expression by 2, so this is 2x sine x, minus I have to multiply this one by nothing. It's already fixed. Nice. And so what happens when I plug in pi over 2? Well, 2 times pi over 2 is pi. Sine of pi over 2 is 1, so this is pi minus pi, which is 0, over the cosine of pi is 0, so that pi over 2 is 0. So that's 0 over 0. And yes, I have to use the product rule in the numerator, but maybe I only have to do it once. Let's see what happens. It's first, which is 2x, d second, which is cosine x, plus second, which is sine x, d first, which is 2. The derivative of pi, hallelujah, is 0 over the derivative of 2 cosine x, which is negative 2 sine x. And then what happens when I plug in pi over 2? Well, the cosine of pi over 2 is miraculously 0, and we get sine of pi over 2, which is 1. So this is 2 over negative 2, which is negative 1. So infinity minus infinity in this case is not 0, it is negative 1. And if I recall, one I did in class had the tangent and the secant, and infinity minus infinity in that case was 0 because they do approach pi over 2 at the same rate, which is kind of cool. All right, last but not least, number 18. Woohoo, one more. All right, that's the limit as x approaches infinity of 1 plus 5 over x plus 3 over x squared raised to the x. Now this is a function of x raised to the function of x, so I'm going to say that that's y equals, and we're going to take the natural log of both sides, so we get natural log of y equals the limit as x goes to infinity of, I'm going to take the liberty of bringing that x down in front, x times the natural log of 1 plus 5 over x plus 3 over x squared. And I have infinity times, well, these terms, 5 over x, 3 over x squared, when x goes to infinity, these terms go to 0, so I get the natural log of 1, which is 0. And when we're in this form, we have to somehow get a fraction, so we take the polynomial, and we put the polynomial in the denominator reciprocated. So this is the natural log of 1 plus 5 over x plus 3 over x squared over 1 over x, and let's see what happens to our expression. Now we have the natural log of 1, because these two terms are going to go to 0, which is 0 over the natural log as, 1 over x as x goes to infinity goes to 0. So I can use L'Hopital's rule here. So we get the limit as x approaches infinity of, well, the derivative of the numerator is the function in the denominator, which is 1 plus 5 over x plus 3 over x squared, with the derivative of this in the numerator. So 5 over x, its derivative is, the derivative of 5x to the negative 1 is negative 5x to the negative 2. And then this is 3x to the negative 2. So that's going to be negative 6x to the minus 3. So I'm going to write it like that. Over the derivative of 1 over x, which is negative 1 over x squared. All right, and I'm going to do a simplifying step. And that's going to be negative 5 over x squared minus 6 over x cubed over 1 plus 5 over x plus 3 over x squared times negative x squared over 1, because I reciprocated to the denominator. And simplifying that, I get the limit as x approaches infinity of, what happens when I multiply x squared in here? Well, I get a positive 5, and the x squareds cancel, plus 6 over x over 1 plus 5 over x plus 3 over x squared. And what happens now as x goes to infinity is this term goes to 0, this term goes to 0, this term goes to 0, and I'm left with just 5. But I have to remember that I took the natural log of this expression in the very beginning, bring down the natural log of y, and I exponentiate, and I get y equals e to the 5th. So my limit as x approaches infinity of 1 plus 5 over x plus 3 over x squared raised to the x is equal to e to the 5th. All right. Okay, so what is this one? This one is 1 to the infinity, and it turns out to be e to the 5th. Okay, so on the test, let's see what I put on the test. I put a 0 times infinity. I put a 0 over 0. You haven't used the product rule. I put an infinity minus an infinity, and I put a 1 to the infinity. 1 to the infinity. So I'm guessing that you're probably going to see something similar in the not too distant future. And so make sure we know how to do those. All right. And that is L'Hopital's rule and as many examples, including the 4 that were on the test, that I could think of at this time. So everybody have a blessed day, and we'll talk to you next time.